Hello everyone, I am Shagnik and my friend Rahul, and we have worked under the supervision and guidance of Professor Sourav Saha to complete the project entitled A Multi-Level Polygonal Approximation Based Shape-Encoding Framework for Automated Shape Retrieval. Coming to the objective of our project, we know that with the increasing number of images generated every day, textual annotation of images for image mining becomes impractical and inefficient. Thus, computer vision-based image retrieval has received considerable interest in recent years. One of the fundamental characteristics of any image representation of an object is its shape, which plays a vital role to recognize the object at primitive level. Keeping this view as the primary motivational focus, we propose a shape descriptive framework using a multi-level polygonal approximation. Such a framework explores different degrees of convexity of an object's contour segments and captures shape features at different approximation stages, as the proposed algorithm determines polygonal approximations starting from coarse level to more refined representation of a closed contour. We have also presented a shape encoding scheme based on multi-level polygonal approximation, which allows us to use the popular distance metrics to compute shape similarity score between two objects. Coming to the related works, image retrieval of this sort has received considerable attention from researchers over the past few decades. One of the earliest attempts in this field is based on global features such as invariant moments, Zernike moments, and also the angular radial transform or ART descriptor. Curvature scale space or CSS is one of the most widely accepted shape representations as proposed by Mokhtarian. It has also been recommended by the MPEG 7 community as the standard for boundary-based shape description. Coming to the overall flow of our project, first we take the image object, then we extract the contour of the object, then we perform the multi-level polygonal approximation, and after that, using the data set that we have in the database, the data set of the images that we have, we perform the shape encoding and then we match with the data set, and finally we get an ordered list of retrieved shapes based on shape matching score. So this is our proposed framework. First we find out the thick polyline approximation of our contour using the optimal thick line, and then we perform the greedy best first heuristic based curve splitting strategy, and then the polygonal approximation. Finally, we use the shape descriptor for multi-level polygonal approximation. So coming to our first task, that is fitting optimal thick line. Given a sequence of discrete 2D points and its convex hull, there exists a valid thick line defined by a pair of support lines L1 and L2, such that L1, this is our line L1, is coincident with an edge EI of our convex hull, that is L1 is coincident with this edge of the convex hull, V1, V2, this edge of the convex hull, and L2 is another straight line passing in parallel with L1, and it is passing through a point of the convex hull, V3 is the point here, and V3 is the farthest point from this straight line, that is from L1. Here there is another point of the convex hull V4, but this is not the farthest point, that is why we chose V3. And this pair V3 and this L1, this pair is called the antipodal vertex edge pair. So basically determining an optimal thick line for D is equivalent of finding an antipodal vertex edge pair for which the antipodal distance is minimum. After our first task of fitting an optimal thick line is complete, we come to our next task, that is greedy best first heuristic based curve splitting strategy. A curve is split into two segments at one of its convex hull vertices Qy, and the vertex at which the curve is split is termed as pivot vertex in our scheme. So here there are two possible candidates for Qy, that is Q2 and Q4. Every convex hull vertex Qy except the curve endpoints can split the curve into two proper segments, but only one of them is chosen as Q2, which is chosen here. So only one of them is chosen based on the optimal criterion as expressed through the following equations. Here split cost, as we are seeing here, split cost denotes the heuristic cost associated for choosing Qy as pivot vertex. So here we can see that Q2 can act as the pivot vertex and Q4 can act as the pivot vertex, but we are choosing only Q2 because it gives us the minimal cost. So we are splitting the curve on Q2 and we are getting these two curves. After that we are again splitting the curve on Q4. We could have also split the curve at Q1, 1, 2, but Q4 gives us the minimal cost, and that's why we are splitting the curve at Q4. In this way we are getting these endpoints, these leaf points, as our final curve splittings. So now coming to the multi-level polygonal approximation, in our proposed framework, users can flexibly specify the number of edges to obtain a thick-edged shape approximating polygon. That is, the users can specify that he wants a polygon of 4 sides or of 6 sides. We have utilized this characteristic to approximate a shape at various approximation levels by varying the number of edges of approximating polygon. Here we can see how the number of dominant points and the edge thickness varies as we change either one of them. So we have seen that if the number of dominant points increase, then the thickness decreases, and the vice versa. We can also see here that as we increase the number of dominant points, our error is decreased, that is, our approximation becomes less. And if we decrease the number of dominant points, then we are more approximating the shape, and it does not give us appropriate result. In the proposed framework, a shape is approximated at multiple stages by varying the number of sides of the approximating polygon, leading to a multi-level shape descriptor feature formation. At every stage, a shape descriptor feature vector is formed corresponding to the respective shape approximating polygon. In our project, we have taken the internal angles of the polygon as our feature, and the internal angles at each vertex is computed as given below. And the new set of computed angles is sorted in ascending order. So here we can see how it works. We are taking different images and then we are calculating the internal angles at every vertex of the polygon, and we are sorting the internal angles in ascending order. We are doing so at different levels of the polygon, that is at number of sides equal to 4 and also at number of sides equal to 6 and so on. Finally we get our feature vector like this. Coming to the dissimilarity score matrix, we are calculating the dissimilarity between two shapes using this formula. As we can see here from the output, that a bell 1 with bell 1 is obviously similar, that is why the dissimilarity score between them is 0. A bell 1 with bell 2 has a slight difference between them, that is why it has a slight bit of dissimilarity score, but a bell 1 with a frog 1 is highly dissimilar, that is why they have a larger value of dissimilarity score. This way we have computed this table. So these are the results that we have obtained. This table presents the performance of our proposed algorithm for the sample data as compared to the popular CSS scheme. We can see here the bullseye score. On the average, the new proposed algorithm results in 85% on bullseye test, which seems reasonably good as compared with existing state-of-the-art algorithms. In order to test the effectiveness of the shape descriptor vector with respect to the proposed similarity metric, we have also performed KNN classification on the dataset and obtained fairly good class prediction accuracy rate as evident from this table. So now it's time for us to see how the actual code works. So let us check the code. So this is our main class, shape-retrieval engine.py. Let us run this code to see the output. Just a minute, it's taking some time, and here it comes. So this is our graphical user interface. Here we can give the query image. We can just browse an image. So let me give the image of maybe a frog. We open the image here. This is our query image, the image of a frog. Now we search this image in the database and we see the nearest images, the nearest 9 images. We search for it and here it comes. Here are the images of the 9 frogs that we have gotten from the database using our algorithm. We can also give another image, that is that of a bird, and we search for it and here we see. It gives us the list of 9 birds that it has got from the database, the list of the 9 nearest birds that represents this shape. We can also see the internal working of it, that is how the polygon is being formed. We can just check for it here. If we run this code, here we see this is the polygon that is being formed of this bird. It is a polygon of 6 sides and we see how the polygon is being formed. So as we have seen the output, now we can just get back to our presentation, and we've almost come to the end of it, and we would like to conclude here. An effective shape descriptive framework called multi-level polygonal approximation is proposed for similar shape retrieval, which exploits different degrees of convexity of an object's contour, and a special shape encoding scheme has also been developed to measure shape similarity between two objects. The performance of the proposed scheme is reasonably good and comparable with existing state-of-the-art algorithms. However, we need to further analyze the robustness of the proposed framework under plausible deformations of closed contours. These are the references that helped us in making the project. So we've come to the end of it, and thank you all for watching.